In this segment, we're going to talk about linear regression, but we're going to talk about a special case of no intercept. So this is the example where you have no intercept for a linear regression model. If you remember that what we are trying to do here in the linear regression with no intercept is given x1, y1 all the way up to xn, yn. Somebody is telling you to best fit now y is equal to a1x. That's it. There is no intercept. There is no a naught quantity in your linear regression model. What that means is that the regression model is going right through the origin, because when x is equal to 0, y is going to be 0 as well. A good example of this can be when you have stress versus strain data. So let's suppose you're taking stress versus strain data for a piece of steel. Let's suppose you're going to get stress versus strain data, then you may have to regress it to sigma is equal to E epsilon. So here there's no intercept in this straight line. This is a special case for straight line where the intercept is 0. So you're going to, this is stress and this is strain. And once you have the stress versus strain, whatever regression you're going to draw, the slope of that line will be simply the Young's modulus. So this is a pragmatic application of why you would want to use a straight line regression model without the intercept. Now if we go back to the formula where we had given x1, y1 all the way up to xn, yn. So this was something which we did previously, that if it's given and somebody says, hey, best fit y is equal to a0 plus a1x. And when we had this, where we had the intercept, then we developed the formulas. We got a1 equal to n times summation x of I, y of I is equal to 1 to n, minus the summation of x of I, summation of y of I, divided by n times summation x of I square, I is equal to 1 to n, minus summation x of I is equal to 1 to n square, and then a naught we got as y bar minus a1 x bar. So this is what we obtained when we had y is equal to a0 plus a1x. So I'm just recapitulating what we had done. This is what we got for a1, this is equal for a naught. Now somebody might suggest that, hey, since a naught is equal to 0, I can just simply use whatever a1 I get here to choose, since a naught is equal to 0, can I use a1 of the above formula? For y is equal to a1x model. The question is that since a naught is equal to 0 for our current model in which we have no intercept, can I simply use this expression for a1, say that, hey, this is my value for a1 for the regression model of y is equal to a1x. And somebody might say, no, why don't you just go ahead and take this one, since a naught is equal to 0, 0 is equal to y bar minus a1 x bar. So this looks nice. So a1 is y bar divided by x bar then. But what is wrong with this? There are a lot of things wrong with this. There are a lot of things wrong with choosing this to be the value of a1 for your y is equal to a1x regression model. So you cannot use this expression for your a1 for your regression model. You cannot choose this one for your regression model. And the reason why that is so is because the way a naught and a1 were found for your linear regression model, which had an intercept and had a slope, was based on the fact that you are minimizing with respect to a naught and a1. You are minimizing with respect to a naught and a1. That's how you got these two expressions. But when you have this simpler linear regression model where there is no intercept, you can only minimize with respect to a1. And since you only can minimize with respect to a1, you cannot use the same formulas as are given here, because a naught is fixed. Your A naught is fixed for your regression model with no intercept because A naught is 0. So you cannot minimize something which is already fixed. So that's why using these formulas are not valid. So I'm going to put a big cross right here. So this is a wrong formula to use. This is a wrong formula to use. So both of these are wrong formulas to use for if your model is y is equal to a1x. So the question arises, how do I find a1? Well, you go back to the drawing board by calculating the sum of the square of the residuals and finding what a1 is. So again here, what's going to happen is that the residual at each point will be the observed value, which is y sub I, minus the predicted value, which will be a1 times x of I, because the value of x at that particular point is x of I. So that is the residual. Now I want to square the residual. That's this. Then what I want to do is I want to sum all these residuals from all the data points, I is equal to 1 to n, and that's what my SR is. So for this model, the sum of the square of the residuals is simply squaring the residual at each point and then adding them all up, just like I had it for the regular linear regression model. Now in this case, in order to find out the derivative, in order to find out a1, all I have to do is to take the derivative with respect to a1 and put that equal to 0. And in this case, it will turn out to be 2 times summation y sub I minus a1 x of I times minus x of I, going from I is equal to 1 to n. So it is 2 times this quantity times the derivative of this inside bracket quantity, parenthesis quantity with respect to a1, which is minus x of I, and that I'll have to put equal to 0. So if I expand this, I get minus 2 summation I is equal to 1 to n x of I y sub I plus 2 summation a1 x of I square I is equal to 1 to n. So what I get by expanding the summation here, the 2 and 2 cancels, and then I can take this to the right hand side because it's a known quantity, and I can take a1 outside because it's a constant. So I'll get a1 times summation I is equal to 1 to n x of I square is equal to summation I is equal to 1 to n x of I y sub I. That's what I'm going to get. And what that this particular equation here, is going to give me the value for a1, which is summation x of I y sub I is equal to 1 to n divided by summation I is equal to 1 to n x of I square. So that is the way you want to find out what the value of a1 is for the regression model y is equal to a1x. So as part of the homework, I'm going to, since we are taking the first derivative, so we took the first derivative with respect to a1, put that equal to 0. That only tells me it is a min or max. It does not tell me whether it is this a1 which you just found out, the a1 expression which you just found out corresponds to a minimum or a maximum. What I would like you to do is to use the second derivative test to show that a1 value you got corresponds to a minimum. So what you have to do is you have to take the second derivative I saw with respect to a1, put that equal, and then substitute the value of a1 which we just obtained, and then see whether that quantity is positive. That will correspond then to a minimum. So that's part of your homework, and that's the end of this segment.